Let us talk about this Ratinamaze problem. We are given a binary matrix which represents a maze. 0 values in this matrix are blocked cells and 1 values are the cells through which rat can move. In this maze, there is a rat at the top left corner and there is a cheese at the bottom right corner, and rat has to collect this cheese. Now rat can go through only unblocked cells. Rat cannot go through the cells with value 0, which are shown here as blocked here. So these cells are blocked and these cells are allowed cells where rat can move. And when rat is at cell ij, it can make only these two moves. It can go to I plus 1j and it can go to ij plus 1. So I plus 1j means the cell just below it, and ij plus 1 means cells which is just on right of it. For example, when rat is here, it can move to this side and it can move to this side. But when the cell is blocked, this move is not allowed, right? So there are two conditions. One is the rat can move only in these two directions, and that too only when these two cells have one value, not blocked, when these two cells are not blocked. So rat has to collect this cheese with these conditions. In this problem, rat can go this way. It begins from here, comes to this side, comes to this side, comes to this side, comes to this side, then goes here, right? I've shown the path here. So this is the path rat can follow and can collect the cheese. Since there exists a path, our output is yes, and we have a binary matrix also as part of the output. The values 1 in this matrix represent the path rat has followed to get the cheese. So the arrows, right? These arrows are represented by these ones, right? So we have represented our output as this binary matrix where 1 means this is the cell which rat followed. Let's see another example. In this example, we have this maze and rat is always considered at the top left and cheese is always considered at the bottom right. So in this example, rat cannot collect the cheese because it cannot move from the first cell itself, right? Because the cell on the right of it is blocked and the cell on the bottom of this is also blocked, right? And rat is only allowed to make these two moves. So the output for this particular input is no. Now please pause this video and try to write down a program that considers this binary matrix as input. It returns a value true or false. It returns true if there is a path for rat. It returns false if there is no path for rat. And if there is a path, then your code should also print this binary matrix to indicate the path that rat has followed. Let us talk about the solution now. A naive solution is to generate all paths from top left to bottom right, then traverse through all the paths. For every path, check if it leads to a solution or not. As soon as you find a path that leads to a solution, you print the solution, return. A better idea is to use backtracking. What we do in backtracking solution, we generate these paths step by step. And while we are generating the current path, and if we find the solution with the current path, we immediately return true. So we do not generate all the paths first. Also, when you are generating the current path step by step, at any step, if you see that these set of steps that we have chosen cannot lead to a solution, then you do not generate any path which starts with these steps that you've already taken, right? So this way you cut down the recursion tree completely. Let us see this code now. In this code, we have three functions. We have one function solve maze, other function solve maze recursive, and third function is safe. So is safe function is generally there in all the backtracking algorithms. When you make a move, you check if this move is safe or not. And if this move is not safe, you do not make the move, you immediately return false, right? So this function mainly calls this function, right? And this is where whole logic of the solution is. And what this function does, it simply calls this, and if this recursive calls returns false, it returns false, otherwise it prints the solution and returns true, right? So it's simply using its return value and printing the solution. This is where our main logic is. And what we do in this function, we take cell location as parameter. We check if this current location is the destination location. If that is the case, we mark the solution as true and we return true. And if this is not the destination solution, we check if this particular cell is a safe cell or not. So what do we mean by safe cell? We check whether this is a blocked cell or not. This is what we're checking here, right? If this is 1, then only it's a safe cell, otherwise not, right? We also check I should be smaller than n, j should be smaller than n. Why are we checking these conditions, I smaller than n, j smaller than n? Because we are making recursive calls here for I plus 1 and j plus 1. And we are blindly making these recursive calls without putting any condition here in I and j. So we check for I and j here in the isSafe function. So once we have checked if the current cell is safe, we mark this cell as a part of the solution. We make a move. And then we check, does this move lead to a solution? After marking this cell as part of the solution, we go to the cell just below it and recursively call for that particular cell. And if that recursive call leads to a solution, we return true. Right? As soon as we find a path, we return true in backtracking. Right? If this does not lead to a solution, then we try the right side cell by doing j plus 1, incrementing the column number. And if that leads to a solution, we return true. If both of these do not lead to a solution, then we backtrack. We say that this cell cannot be a part of the solution and we return false. Let us understand the code with this example. So I have drawn a recursion tree here for this example maze, and in this example maze we have this solution, right? We are at top left and we need to reach here, and we need to reach using below move and right move. So we first make the below move, then right move, then below move, then right move, and we reach here. In this recursion tree, I've used a shortcut SMR for solve maze recursive, right? And our initial call is for 0, 0. So when you make a call for 0, 0, what happens? These conditions are checked. Whether this is the destination, it's not. It's safe. Yes, it is safe. It's smaller than n. I and j both are smaller than n. So you mark it as part of the solution. You mark solution of 0, 0 as 1. And after marking the solution, you make first recursive call as 1, 0, the cell just below it, right? So when you make this recursive call for cell just below it, this also makes a recursive call for cell just below it, because this also begins the execution from first line, yeah, and goes to these things and then makes this recursive call. And when this recursion call is made, you have made a call for 2, 0. What happens for 2, 0? 2, 0 is not a safe cell because its value is 0. So isSafe function returns false here, right? And since isSafe function is returned false, you come here and you return false. So this recursive call returns false to its parent call, right? Now the control comes back to the parent call and it makes the recursive call for the right side. It has already made the recursive call for the below side. Now it makes a recursive call for the right side. So you again begin execution with 1, 1, right? When you begin with execution 1, 1, 1, 1 is not destination, it's safe. So you come here. So you make a recursive call for the below cell for 2, 1. When you make a recursive call for the 2, 1, it also makes 2 recursive calls, first for 3, 1. And when a recursive call for 3, 1 is made, what happens? 3 is not a safe cell. 3, 1 is not a safe cell because it is equal to n. N is 3 here in this example, right? There you have 3 rows and 3 columns. So you return false from this recursive call. This recursive call returns false. So the parent, it tried the cell below it. Now it's going to try the cell on the right side of it. So when it tries for the cell on the right side of it, what happens? You call for 2, 2. And 2, 2 is your destination cell. So you return this as true. So this returns true to its parent. And before returning true, it marks 2, 2 as 1. Right? So in your solution cell, in your solution matrix, which is a 3 cross 3 matrix, you mark this as 1. And before you had called for this, you must have marked this also as 1, right? That's what we do before making a recursive call. So 2, 1 also marked as 1. 2, 1 is this one. And this parent must have marked 1, 1 also as 1. And this parent call must have marked 1, 0 as 1, right? So this must have been marked as 1. And this call must have marked 0, 0 as 1. So you get your appropriate solution matrix, which is the output path, right? And how do these return values work? See, as soon as it finds a solution here, it returns true to the parent. And parent, as soon as it finds a true value from a child call here, the parent must have been here. As soon as it finds a true value, it returns true to the parent of itself, right? So it returns parent of it as true, right? And this parent, again, it finds a return value true by its left call, so this also returns true to its parent, right? And this call has found a return value as true by the right call, so this also returns true to the parent. And finally, this also returns true to the main function. So we return true as overall output, and our solution matrix is also appropriately updated.